So far we have looked at work and energy separately. This time around we want to combine them into one theorem called the work energy theorem. How does this state? It states that the work done by the resultant external force on a body is equal to the change in the kinetic energy of that body there. How do we prove this? We can simply say that assuming that you have a body of mass m, and this body is acted upon by a constant force F, and as a result it moves through a distance which I may call distance S in a given time t. So at the same time its velocity changes from the initial velocity u to the final velocity v after having traveled a distance, after having traveled for a time t. So from the definition of work done, we've already said that the work done is given as the product of the force and the distance moved in the direction of the force. But remember that the force F from Newton's second law of motion is given by F is equal to ma, and also from the third equation of motion that v squared is equal to u squared plus 2as, I can make my s subject of the formula. It implies that this is the same as s equals to v squared minus u squared out of 2a. So if this is my equation 1, this is my equation Roman 2, substituting those two equations, Roman 1 and Roman 2, into equation which I'm calling star, I'll end up with work done being equal to the force F, which is ma, times v squared minus u squared out of 2a. So we can say this a cancels out with this a, and we end up with w, which is the work done, equals to a half times the m into v squared minus u squared. Expanding that will give us work done is equal to a half mv squared minus a half m u squared, and this is the final kinetic energy, this is the initial kinetic energy. So we see that the work done is actually equal to the change in the kinetic energy of that body there. Now this statement here basically works for a situation where we have only the driving force F and no any other force acting on the system. Otherwise, if there is maybe friction, maybe there is air resistance, maybe there is viscous drag, then the phrase changes a little bit. So in short, we can say that the work energy theorem is the same as getting the total energy at point A and the total energy at point B. All those ones must be equal. All those must be equal. And the change in energy is always equal to the work done. Let's have an example here and we see. So the question says that brakes are applied to a car of mass 5,000 kilograms, and as a result it decelerates on a level road from a velocity of 4 meters per second to rest after traveling for 1 meter. Determine the braking force. So when we're answering this question here, of course we said that the first thing to do is always to summarize what has been given to you. So we have our mass as 5,000 kilograms, we have our initial velocity as 4 meters per second, then we have the final velocity as 0, it went to rest, and then we have the distance traveled as 1 meter. Calculate for the braking force. So assuming that we have our body like this, and if the brakes are applied, it means that there is no driving force. So our driving force, which I may call D, is equal to 0. And then we have the braking force which acts in the opposite direction. I will use my F. So if the resultant direction is that, force on this body here also have the weight, which is equal to mg, and at the same time also have the normal reaction R. So maybe the braking force is due to the frictional force and as well as the brakes of the vehicle. So using the equations that from the second law of motion, our resultant force F equals to ma, we can say that the resultant force in this case is 0 minus the backward force, which is the F. Everything is equal to ma. And we have the mass, we don't have the acceleration, but we can get the acceleration from the third equation of motion. V squared is equal to u squared plus 2as. Our final velocity is 0 squared. The initial velocity is 4 squared plus 2 times a times the 1 meter, which implies that our acceleration a is actually equal to negative 8 meters per second squared. 4 squared, that is 16 divided by 2, that is 8 meters, negative 8 meters per second. So when I substitute this into the other equation, I'll end up with my negative f equals to 5,000 times negative 8. And the answer that I get will be a positive f, meaning that the braking force F is equal to 40,000 newtons. And that is my force. Now, that is using the normal way. Let's try the same question using the work energy theorem and we see what we do get. So using the work energy theorem, we're having two locations, the initial, which is A, and then the final location, which is B. And at the final location, the body has moved through a distance which is S, which is 1 meter. And the final velocity here is 0 meters per second. And the braking force has moved through that distance S. Of course, this one is still 0. Now, from the work energy theorem, which says that total energy at A must be equal to total energy at B. And at A, we're having only kinetic energy, which is a half mv squared. And at B, we're having also 0 kinetic energy. I'll use a half mv squared. Let me use u here, initial velocity. And then since this force F has moved through a distance S, we shall also add on the work done against that. The force F has moved through a distance S. So it has done some work. So remember that we said that work and energy are the same. And in this case, that's why I'm having the kinetic energy and also the work done against this resistive force here. So if I'm substituting to the values, I'll be having my a half times the mass, which is 5,000, times the initial velocity, which is 4 squared. This one must be equal to a half times the mass, which is 5,000, times the final velocity, which is 0 squared. Then plus the force that we need times the distance, which is 1 meter. When you solve this equation here, you'll find out that your F is equal to 40,000 newtons. So this is another way of solving this equation. So whenever using the work energy theorem, simply say that the total work or total energy at A is always equal to total energy at B. If there is only one force, which is the resultant force, then you can simply say that the change in the kinetic energy of the body is always equal to the work done by that force F. That is what we can do using this.